Here in this section we have solutions, slope fields, and Euler's method. The first part, general first order differential equations and solutions. So here, first order differential equation is an equation dy over dx that is equal to f of x comma y, in which f of x comma y is a function of two variables defined on a region in the xy plane. Solution of this equation is a differentiable function y equal to yx defined on an interval I of x values such that d over dx yx is equal to f of x comma yx on interval I. So that is when yx and its derivative y prime x are substituted into this equation. The resulting equation is true for all x over interval I. The general solution to a first order differential equation is a solution that contains all possible solutions. The general solution always contains an arbitrary constant. So here we have constant, but having this property does not mean the solution is the general solution. A solution may contain an arbitrary constant without being the general solution. Here on this board, as with antiderivatives, we often need a particular rather than the general solution to first order differential equation y prime equal to f of x comma y, the particular solution satisfying the initial condition y x sub 0 equal to y sub 0 is the solution y equal to yx. This value is y sub 0 and when x equal to x sub 0. So the graph of the particular solution passes through the point x sub 0, y sub 0 in the xy plane. The first order initial value problem differential equation y prime equal to f of x comma y. The solution must satisfy an initial condition y x sub 0 equal to y sub 0. So here we have xy and we have this point x sub 0, y sub 0. And this curve, here we have y equal to yx. And this line y equal to lx, and that is equal to y sub 0 plus f of x sub 0, y sub 0 times x minus x sub 0. So again, here we have x sub 0, y sub 0 is this point, and here on this part we have this point that is x sub 1, comma y x sub 1. Here on this part we have dx. This point is x1. So here we have x sub 0. Here we have x sub 1. That is equal to x sub 0 plus dx. So this point is equal to what we have here, x sub 0 plus what we have on this part. So in this part, what we did was based on these 2 points, x sub 0, y sub 0, and this point here on this line, x sub 1, y sub 1. Now we're going to use these for Euler approximation. So here we have x0, x1, x2, x3. And these are based on these points that we have here. x0, y0, x1, y1, x2, y2, x3, y3. And here we have between x sub 0, x sub 1, here we have dx. So between these two we have dx, and here we have dx. So finding what we have for x1, x2 up to xn. So x1 is equal to, this point is equal to what we have before that. It's x sub 0 plus dx. X sub 2 is equal to x1 plus dx. up to xn is equal to xn minus 1 plus dx. And based on these, what we have for y1, y2, yn, y1 is equal to y0 plus f of x0, y0 times dx. y2 is equal to, so changing from y0 to y1, and from x0 to x1, y0 to y1. So we have exactly the same thing, but we're changing from y0 to y1 and x0 to x1. And for yn, that is equal to yn minus 1 plus, here again we have n minus 1, so it's xn minus 1, yn minus 1. Then here we have again dx. So what we had here for the first part, y1 equal to y0 plus f of x0, y0 times dx. That is what I have here. It's same as finding a slope. So y1 minus y0, I move this to left side. That is equal to f of x0, y0 times dx. Now isolate f of x0, y0. That is equal to dx over y1 minus y0. And dx is what we have here on this part. dx is equal to x1 minus x0. So f of x0, y0 is equal to x1 minus x0 divided by y1 minus y0. So this is what we have for slope. Example, write an equivalent first order differential equation and the initial condition for y. Y equal to 6 plus integral from 2 to x t minus 4y t times dt. So the first order differential equation is the equation dy over dx equal to f of x comma y, in which f of x comma y is a function of two variables defined on a region in the xy plane. Take the derivative of each side of the equation with respect to x. So what we have here, y prime is equal to 0 plus d over dx integral from 2 to x t minus 4y t times dt. In the given equation, so here on this part, f of t comma yt is t minus 4y, so is this part. Therefore y prime is f of x comma yx. So based on what we have here, y prime is equal to x minus 4y. So again, f of t comma yt is equal to t minus 4y. And y prime is equal to f of x comma yx. So instead of t, here I have x. And based on that, y prime is equal to x minus 4y. So what I did, instead of t, I used x here to find y prime. So y prime equal to x minus 4y as the first order differential equation for the given equation. Now we have to find the initial condition by determining the value of x sub 0 and y sub 0. So here on this part, x sub 0 is the lower limit of the integral in yx equal to y sub 0 plus integral from x sub 0 to x f of t comma yt times dt. In the given equation, the lower limit of integration is 2, so x sub 0 is 2. So this one was the answer for first order differential equation, and this one was for initial condition for y. Use Euler method to calculate the first 3 approximations to the given initial value problem. For the specified increment size, calculate the exact solution. dy over dx is equal to 9xy plus 3y, y0 is equal to 6, and dx is equal to 0.1. So here on this part, we're going to use this formula yn equal to yn minus 1 plus f of x sub n minus 1 comma y sub n minus 1 times dx. So the first part here is to calculate the first approximation, y1. So y1 is equal to y sub 0 plus f of x sub 0 comma y sub 0 times dx. What we have for y0, that is 6 plus And here for dy over dx, that is equal to f of x comma y. So here we have 9 times x is 0 times y is 6 plus 3 times y sub 0 is 6 times dx. So that is 0.1, and this is equal to 7.8. Now use x sub n equal to x sub n minus 1 plus dx to find value of x sub 1. So x sub 1 equal to x sub 0, that is 0, plus dx, it's 0.1, so this is equal to 0.1. Now find y2, so that is equal to y1, from first part y1 is 7.8, plus so here using this part, 9 times xy plus 3y. So 9 times x1 is 0.1, times y1 is 7.8, plus 3 times y1, 7.8, times dx, it's 0.1. So this is equal to 10.842. Now find the value of x2 is equal to x1 plus dx. So that is equal to 0.2. Now find y3 is equal to y2. So it's 10.842 plus 9 times y2 x2. So here x2 is 0.2 and y2 is 10.842. Then plus 3 times y2 times dx. So y3 is equal to 16.0462. To find the particular solution of the differential equation, integrate both sides of the equation to find the general solution. Then solve for the arbitrary constant using the initial conditions. So here we begin by separating the variables, what we have for dy over dx, that is equal to f of x comma y, and f of x comma y is 9xy plus 3y based on what was given here on this part. Now factor out y on the right side. So dy over dx is equal to y times 9x plus 3. Divide both sides by y and multiply both sides by the differential dx. So what we have here, dy over y is equal to 9x plus 3 times dx. So using what we have here on this part, for dy over y, set up the integral on both sides of the equation. So here we have integral y 1 over y times dy equal to 9 integral x dx plus integral 3 dx. Now integrate on both sides of the equation. So here on this part we have 1 over y. So integrate, that is natural log absolute value of y, and that is equal to, here we have 9 integrate x, so that is x squared divided by 2 plus, here we have 3, so that is 3 times x plus c for constant. Now simplify the equation. So natural log equal to what we have here on this part. So I'm using e on both sides. So exponentiate both sides of the equation. So this is equal to e. Now writing what we had here on this part, it's 9x squared divided by 2 plus 3x plus c. So I simplify. So this part cancels, and what we're gonna have is absolute value of y is equal to what we have on right side, so e power 9x squared divided by 2 plus 3x plus c. Recall that absolute value of y equal to x, what that means for y we're gonna have negative and positive values, so y equal to negative positive x. So here in this case we will have y equal to negative positive e power 9x squared divided by 2 plus 3x. So rewriting this part, here we have y equal to negative positive e power c times e power 9x squared divided by 2 plus 3x. So here replace negative positive e to the power c with another constant a, for example a, and then simplify. So this one, y equal to, so instead of negative positive e power c, I'm using a. Then we're gonna have e power 9x squared divided by 2 plus 3x. So this is the general solution of dy over dx. And that is y equal to a times e power 9x squared divided by 2 plus 3x. Now use the given condition of y0 equal to 6 and find value of a. So this is what we have for y. And that is equal to a times e power 9x squared divided by 2 plus 3x. Now y0 is 6. And that is equal to a times e power 9x is 0. So x sub 0 is 0. Divided by 2 plus 3 times x sub 0 is 0. Solving for a. So here power is 9 times 0 plus 3 times 0. So that is 0. So 6 equal to a times e power 0. So a is equal to 6. Now substitute the value of the constant a into the general solution found earlier to find the exact solution to the differential equation. So what we have here, y exact value, so that is equal to 6 times what we have for a is 6 times e power 9 x squared divided by 2 plus 3x. So this is what we have for exact solution. Use the Euler method to calculate the first three approximations to the given initial value problem for a specified increment size. Calculate the exact solution and investigate the accuracy of your approximation. So what is given here on the spot, y prime is equal to 3 times x squared times e power x cubed, y0 is equal to 10, and dx is 0.25. So what is given on this part, we have x sub 0 is equal to 0 and y sub 0 is 10. Now evaluate f of x comma y, which is equal to dy over dx. So dy over dx is equal to f of x comma y. Evaluate this for x sub 0 equal to 0 and y sub 0 equal to 10. And I'm going to run to 6 decimal places to reduce numerical errors. Keep more decimal places than are required in the final solution for all the intermediate calculations. So here in this case, I'm going to have 6 decimal places. So what do I have for f of x sub 0, y sub 0 is equal to 0. So f of x sub 0, y sub 0 is equal to 3 times x sub 0 is 0 squared times e. Again, here we have 0 for x sub 0 cube. So this is equal to 3 times 0 e power 0. So that is 0. I'm using 6 decimal places. So it's 0.000000. Now use x sub 0 and y sub 0 and dx to find x1, y1, again rounding to 6 decimal places. So x1 is equal to x sub 0 is 0 plus dx is 0.25. So x1 is equal to 0.250000. Now finding y1, that is equal to y0 is 10. F of x sub 0, y sub 0 is 0 times dx is 0.25. So what we have here for y sub 1 is equal to 10.000000. So here again I have 6 decimal places. Now using what we have for x1 and y1, find f of x1 comma y1, that is equal to 3 times x1 squared times e x1 cubed, and this is equal to 0.190453. The next step, find x2 and y2. So x2 is equal to x sub 1 plus dx. X sub 1 is 0.25 and dx is 0.25. So here x2 is 0.50, but here again I used 6 decimal places, so it's 0.500000, and y2 is equal to y1 is 10. F of x1, y1 is 0.190453 times the x is 0.25. So what we have for y2 is equal to 10.047613. And based on that, now finding f of x2, y2, that is equal to 3 times 0.50 to the second power times e, 0.50 to the third power. So here power for e is 0.50 cube, and this is equal to 0.849861. Again, I've rounded to 6 decimal places. Now finding x3 and y3. So x3 is equal to x2 plus dx. So x3 is equal to 0.75, and y3 is equal to y2 is 10.047613 plus f of x2, y2 is 0.849861 times dx, which is 0.25. So y3 is equal to 10.260078. Again, I rounded to 6 decimal place. So here, what we had is x1, x2, x3, y1, y2, y3. So the first three approximations, if we want to run to four decimal places, are y equal to 10.0000, y2 is 10.0476, and y3 is 10.2601. So find the exact solution to the problem by solving the differential equation and compare the approximations to the exact values. The differential equation dy over dx equal to 3x squared times e power x cubed. We can solve this one with u equal to e power x cubed and du equal to 3x squared times e power x cubed. So here we have 3. So we're going to have 3 times x power 3 minus 1. So this is what we have here, 3x squared times what is given here on this part for u. We have e power x cubed. So here for du, we have 3x squared times e power x cubed. So based on what we have here on this part, y is equal to e power x cubed. So use that one. Then add constant. So therefore the general solution is y equal to e power x cubed plus c. Solve for c by substituting x of 0 equal to 0 for x and x of 0 equal to 10 for y. So here on this part what I used was x of 0 equal to 0 and y sub 0 equal to 10. So 10 is equal to e power 0 cubed plus c. 10 equal to, here we have 1, so e power 0, that is equal to 1, and we have plus c. Solving for c, c is equal to 9. So the exact solution is y equal to e power x cubed plus c. Now finding y1, y2, y3 for exact solution. This is equal to e. Here we have x1, so that is 0.25 cube plus 9 running to four decimal places, 10.0157. Now finding y2, that is equal to e power is x sub 2 is 0.50 cube plus 9, that is equal to 10.1331. Y sub 3, that is equal to e power x sub 3, that is 0.75 power 3. So here we have e power is x cubed plus 9, that is equal to 10.5248. Again, I run it to four decimal place. So these are what we have for exact solution. So here on this part we have values for x1, x2, x3, y1, y2, y3 for Euler approximation for exact solution, y1, y2, y3 and the third column. And here to find error we have to subtract what we have for exact solution and Euler. So subtract these to find what we have here in this column for error and error. For the first part we have 0.0157. Second part we have 0.0855, and third part we have 0.2647. So all these were rounded to four decimal places.